All right, well, let's start. First of all, thank you all for coming. As I warned you, it's going to be a somewhat convoluted and confusing talk, and that's just the nature of the problem. And there are two ways of dealing with it. Try to make the material less confusing, or try to make you change your mind frame so you're kind of more used to living with confusion. And we're going to try to meet somewhere in the middle. So I'll try to ease you into why we're talking about RCUs and why they're interesting. So the starting point is we want high performance. For high performance, we need effective utilization of our processor resources, which means often we need concurrency to keep all of these cores busy. Now, sometimes you are lucky and you get it easy and you have read-only data and a lot of computation that you do on it. Now, if you're doing computations, presumably you're interested in the results, so not everything is ever read-only, but let's assume that the results are infrequent, small, so locking and writing the results isn't a concern. So you have huge amount of read-only data, and you just send all your cores doing their processing on it, and it's perfect scaling, go wild. Basically, you have multiple reader threads or consumer threads. They're consuming the data. There is no synchronization. And why there is no synchronization? Because in order to have a race condition, you have to have at least one write somewhere. If you have no writes at all, there is no race condition. You're just reading. So that's the ideal case if you live in this world. It actually does happen, especially in scientific computation, where you have models running for a very long time and inputs don't change. But much more often than that, what you have, well, first of all, let me show you that it actually does scale pretty well. This is a trivial kind of simulation of a simulation. I'm just searching for data in a read-only list on multiple threads, and just the more threads I get, the better it goes. They're just reading the list never changes. To make sure that it actually scales well to a large number of threads, I actually put it on a large machine with a lot of independent cores. Testing on a very large server does, it has its advantages. Like you may say, it's sometimes, okay, it may be not realistic for your 4-core machine, but it does let you see all the things you otherwise might get away with. If you have a small little serial piece of code that takes 1% of your overall computation on a 100-core machine, that's like half of your computation. So you're basically using at most 50% of your large expensive machine if you have that. On a 4-core machine, you wouldn't notice. So if you want to really stress test your code, the more hardware you can throw at it, the easier it is to see what you're doing poorly. Now, if your life isn't quite that easy, there is a much larger domain where data is almost read-only, which means it changes, but it doesn't change very often. So you have a lot of readers that do their heavy computing, and you may be able to get away with a single writer just because you don't have that many writes. It may be easier to have kind of one writer at a time. And multiple threads can write, but you just have a log, so only one thread plays writer at any given time. Sometimes you just have one writer thread. And it's not a concern because you're not bandwidth limited on writes. You're limited on reads. Now, ideally, what you would like is, let's say you have gigabytes of data, and once per hour you update a few bytes. It stands to reason that it should be practically the same as read-only as far as readers are concerned. At least that's what you would like. But there is a problem getting there, because even if writes happen very early, there is a potential for the race condition, which is somebody is reading while you're writing. And if you don't do anything about it, it's a data race. And if you don't do anything about that, well, technically you are in an undefined behavior world. How often have any of you seen the simple solution to it, which is it's once per hour, Let's hope it doesn't happen while I'm running. Now, assuming that that doesn't work for you, you still don't want the readers to wait on each other. You don't want the readers to wait on the writers. Ideally, you wouldn't want the writers to wait on the readers either. After all, it's one write per hour. Why wouldn't you let me do it like right now when I want it? Well, you obviously don't want any locks in this system. So how about a lock-free implementation? Well, there are lock-free lists. I wrote one. It's based on atomic shared pointers. And there it is. It actually does scale, but it's just much slower overall. Now, it's not a fair comparison. It's not a fair comparison because a lock-free list based on atomic shared pointers is a very generic solution. It supports multiple writers. It supports heavy write workload just as well or just as badly as a heavy read workload. It doesn't really care one way or the other. It's a good solution for the problem that it solves well, which is if you have basically writes and reads in about equal amounts going at the same time. But it's a wrong choice when updates are errors. It's not that it's a bad code, it's just it's a wrong tool for the job. Well, we know the right tool for the job, the read-write locks, that's what they're for. Multiple readers, few infrequent writers. Okay, let's put the read-write locks and let's not do any writes yet. This is just the readers. So writes could be happening, but aren't actually happening. So the readers do take read lock, but the writer thread is not running. Well, that's the performance already. Now I'm going to turn on the writer thread. It got a little worse, and then kind of when you have more readers, it's pretty much washed out. At least that's what it did on this machine. I'm just using the POSIX read-write locks. You could do a more efficient read-write locks, but still it's clear that there is overhead on the readers. And there is overhead on the readers even if you don't actually have writes. So, which is like this is really like a big slap in the face. Just for the possibility that tomorrow somebody might write into this data, I'm paying like more than an order of magnitude in performance. And that's before tomorrow actually arrived. Now, the reason is you have to avoid that potential race condition, and you really, really don't want to pay for it. Well, think of this presentation as a concurrent application. I'm the only one who can advance the slides, but you're all reading it. Do you block each other from reading it? No. Whatever I publish here, you can read at your own speed as long as it's still presented, basically until I run out of space. So something like that is what we want. Let's switch tracks now. Sometimes you go to a store, okay, I want a snack. What's the best that I can get for $1? So that's kind of the other approach we're going to take. What's the cheapest atomic operation? Just to show that it's not all 120 core machines, I did this at home on my desktop, just to demonstrate that the conclusions are pretty universal. The atomic read at the top, that's just read, there are no writes, so I'm just reading from multiple threads atomically. The one right below it is one thread is writing, everybody else is reading. And way down there are all the other options like spin locks, mutexes, comparex, and swap, and so on. So it's pretty clear that atomic reads and atomic writes are by far outperforming whatever other synchronization mechanisms you may want to try. So what can we do with just atomic reads and just atomic writes? Well, we can do something like this. So we have this list, and let's say our write is we want to stick a new node into it. So our readers just start from the head and search in the list. Our writer, we have only one, comes in, creates new node. So far nobody cares, it's not visible to anybody yet. Takes the, I'm going to replace the node at the head, so I'm going to change what the first node is, the value. I'm not going to go and actually write into the node and change what's in it. I'm going to create a new node, all of my own in the writer. I'm going to point it to the same thing that the node I'm replacing points. I'm going to put new data into it. Okay, so far there is no race condition, there is no contention because I haven't done anything shared yet. Now I have atomically updated the head to point to the new node. I didn't do any compare and swap, I didn't do any exchange because I'm the only writer. Remember, there is no synchronization of writers yet. The writes are so infrequent that we have only one writer and it's fine. I did atomic write into the head, and now anybody who starts scanning from the head will suddenly see, okay, list doesn't start from old node anymore, it starts from the new node. Well, the readers, as they search, will either see the old value or the new value of the node, which is normal for concurrent data structures. You kind of see the past and the future all at once. That's not unusual, but there are no race conditions in here. I avoided, basically, this is a well-defined program. There is no undefined behavior here, and all I had to do was atomic read and atomic write. Well, I didn't quite do it carefully enough. If you were in my talk on Monday, I told you that if you feel pressed enough to reach for atomics, you should reach all the way. So let's do it a little bit more carefully, look at what you actually need. You basically need an acquire barrier on the load, so you make sure that any writes that were done before become visible to you. And what were the writes that you care about that were done before? Whatever value I put into the new node, when you get the pointer to the new node, you want to make sure that you see the new value. You wouldn't want to see an initialized memory just because you didn't take the memory barrier. One memory barrier is never enough. There's always two. It's a cooperative game. So if there is an acquire on the reader side, there must be a release on the writer side, and the release is when I release the new node into the wild. So when I store the new value onto the head, I have to release it. Again, this doesn't synchronize the writers. Okay, so let's look at what's happening here, kind of take it step by step. Well, the reader, there isn't really any steps. You just read the head and scan. On the writer, there are actually 3 separate actions. I can read the current data, what's there. I'm going to copy it to the new data, at least partially. I'm going to modify it. So I copied the next pointer and I modified the value. I may or may not have used the old value to compute the new value. And then I updated the current data. I updated the head pointer in this case. So read current data, copy it to the new data, update the current data, read, copy, update. That's what RCU stands for. It's actually very confusing terminology because RCU, that protocol that I have just shown you, that scheme of read, copy, and update, isn't really what makes RCU RCU. It's kind of somewhat of a misnomer. In Java, they call this thing CopyOnWrite. In C++, we have the words CopyOnWrite, and they mean something entirely different. As far as I know, there is no universal, commonly accepted term for this. I have seen the words publishing protocol, and that's what I'm going to use. So publishing protocol refers to this protocol where I may read the old data if I need it. I'm going to copy it to the new data, I'm going to modify it, and then in a single atomic transaction, I'm going to reveal it, publish it to the world. Now, more generally, it's not always a pointer. So in general, this publishing protocol involves the use of something I will call a root pointer, and it's not always actually a pointer. It could be, for example, an index into an array. But it's something that if you have it, it gives you access to the rest of the data. That root pointer must be atomic. Readers acquire it atomically, and then it gives them access to whatever data the root pointer reveals. Writers can do whatever they want on their own, prepare the new data, make it all ready, and then they atomically update the root pointer, revealing the data to the readers. That's, in general, the RCU protocol. We'll see in a moment another version of it. Some readers see the old data, some see the new data. That's not uncommon. Okay, let me show you a practical example, and that's actually an example that some of you may have done and some of you may have even done accidentally. the problem here, so let's look at the problem. I want a array-like or a vector-like container. I want it to grow. Grows are infrequent, so it's okay to lock the resize. I don't resize it very often. But indexing happens all the time by many, many threads, so I definitely don't want to lock the square bracket operator. I also don't want to invalidate pointers or iterators, which is kind of it's not directly the same as saying I don't want to log the square brackets, but it's related. So how do you make a growable container that doesn't invalidate pointers or iterators? Well, everybody knows how the basics are, right? Okay. On one thread first, just without threads. It's a block allocated container. It's like a deck. So here is the simplest implementation. My data is stored in the blocks of fixed size. The container itself, the object, has a pointer to a reference block. The reference block, this block of memory over here, has pointers to the data blocks. The container has a pointer to the reference block and has a size. That's how many elements I actually have alive. It has capacity if it was other things, but we're interested in the size. So if you want to grow it, you just add allocate another data block, add a pointer to the reference block, and you got it without moving any data. You didn't move any of the existing data, all your pointers are valid, everything is fine. Okay, so resize adds one block or maybe more blocks if you're resizing by a lot. Old blocks never move, old data never moves. Operator square bracket does need one indirection in order for you to get to from the index. You have some index I, give me the element number 5. Well, first you have to figure out which data block it's in, which means you apply them, you do the modulo to get the index of the block, and then you do the remainder to get the position of the data in the block. If you take one thing away from this talk, please don't do this as written. Make the size of the block a power of 2 and use bit arithmetic. I don't want to be responsible for proliferation of module operators and like 100x slowdown of all the code that uses the DEX. Okay, the same thing now, but with threads. Again, a writer is not multi-threaded. One writer publishes the new block. It's the same thing as publishing protocol. I prepared the new block, I put some data into it, and then I revealed it, published it by storing the pointer in the reference. In the reference block, except that hasn't actually revealed it to anybody yet. It's just a preparation step. What actually reveals the existence of this data to the rest of the universe is updating the size. So size plays the role of the root pointer here. When I update the size, that is the signal that you can access that many elements. Until I update the size, you don't know whether it's safe for you to access these new elements. So you can only access as many elements as the size tells you are present. So the root pointer here isn't actually a pointer at all, and the thing that is a pointer right next to it isn't the root pointer. I'm still going to call it the root pointer. Maybe a root token would be a more generic word. Basically, it's the thing that lets you access the data that is safe to access. So size here tells me what is safe to access. Operator square bracket is not locked. Now notice that the readers, I'm assuming that the readers don't write into the square brackets, or if they do, they somehow synchronize on their own. For simplicity, let's say they don't write into it. So this doesn't synchronize two threads trying to write into the same element. It does synchronize one thread growing while another thread is reading the stuff that was there before the grows. Okay, so we keep growing and we keep growing, and what happens when the reference block is full? We don't have space for any more pointers to the data blocks. We do the read copy update. We allocate a new block that's bigger, copy the old pointers, add a new data block pointer, and we're done. And that still doesn't invalidate any pointers or iterators to the data because data blocks haven't moved. We're still fine. one slight problem. What happens to the old reference block when we're done using it? Well, that's easy. When we're done using it, it's not being accessed anymore. We delete it. So now, well, we delete it. So what do the readers do? First, they split the index into the block index and the data index, not using the module operator as shown on the slides. Then they get the pointer to the data block using the block index, and then they get the data itself using the data index. What happens if the writer is going on at the same time? The reader is doing what I just had on the previous slide. I just abbreviated it on the left. The writer allocates a new reference block. That's fine. Copies the old reference block pointers to the new block. No problem. Stores the new, changes atomically P to point to the new reference block. Go for it. Deletes the old reference block. Now we have a problem. Because the reader may be in flight, in process of evaluating the square bracket operator, and it may be holding a pointer to the old reference block just as I delete it. Of course, the resize happens only once an hour, so probably won't happen to you. Most likely, probably. At least not until you go present it to the customer. Okay, well, now that we worked out through the problem, it's easy to see kind of the requirement. The writer should not delete the reference block as long as there is at least one reader that can access it. Fortunately, the readers don't stay on the reference block for long. It's all encapsulated inside the square bracket operators. Once square bracket operator finished evaluating, the reader will give up the pointer to the reference block. It's a local variable inside the square bracket operator. It's only alive for like a few nanoseconds out of the 1 hour between the resizes. What are the odds of you actually hitting that? I actually had a container which had that bug. And the odds of hitting that were such that it didn't show up until the container reached 1.5 terabyte in memory usage. And then I had to debug it this on a program whose working set was 1.5 terabyte in just that container. And I couldn't reproduce it on anything smaller because it wasn't happening often enough. So soon after the resize, all the readers will finish evaluating the square bracket operator and we can delete the reference block. How soon is soon? Well, that's what the rest of the talk is basically about. But the general point is, it's always the delete that gives you the problem. Lock-free algorithms, ABA problem in the lock-free list, same thing. Without the delete, there is no problem. It's always the delete. Hazard pointers, same thing. If you didn't have delete, you wouldn't need to worry about the hazard pointers. Now, and why do we delete? Well, in general, because even if I could project on the walls and on the ceiling and on the floor and you could all read all my slides at the same time, eventually I would run out of space for projecting slides and I would have to delete some slides and some of you might still be reading them. I could try be more efficient with memory and compressing stuff, but eventually even that hits the limit. So sooner or later you will have to reclaim the memory, most of the time. The solution for that deck container, an acceptable solution for that deck-like container, is actually what? Not to reclaim the memory. If you do the calculation of how much memory you're using for the block of pointers compared to the data, you'll find that it's negligible. The easiest solution to that problem for that particular container is to never delete old reference blocks, period. The memory overhead is negligible, you will never notice, if you choose the size of the data block sufficiently large. But that's not always possible. Usually it's not possible. So the problem, as I said, is not unique to the RCU, but the solution is. And that's what we're going to work on. Again, confusing terminology. The solution that is unique to the RCUs is actually what makes RCUs RCUs. That solution has very little to do with reading, copying, or updating. But that's what makes it really an RCU. You can, if you want, use publishing protocol with atomic shared pointer. reclaiming memory by atomic reference counted shared pointers, but using publishing protocol to reveal the memory. There is a way to do it, it will work, but it's not RCU. It uses the read, the copy, and update, but it's not an RCU. That's just how the name is. Okay, so what's the actual RCU? The key of the RCU is it uses this cooperative protocol, not so much to publish the new data, although it implies that you're not changing data in place. Yeah, RCU implies that you're not changing data in place, you're using the publishing protocol. You create a new copy, update it, and then publish it. That's a given, but that's not enough. Reclaiming memory has to be done using this cooperative handshake protocol. The reader must follow these steps. And that's on the reader. There is really no way to enforce it. You have to call RCU ReadLock, which is some function on your RCU system, to request access to the shared data. Either as a result of calling that function or right after, you can get this root pointer. You have to not use the old copy which you got from the previous call of RCU ReadLock. That's on you. That's the discipline that you have to commit to. And you have to not access that shared data by any other means except through that root pointer or root token in general. Which means you may have an old pointer to some data and it gives you access to the shared data. Don't use it. When you call ReadLock, you have to re-request access to the root and traverse from the root all the way down throughout the data to whatever you want to be. When you're done accessing shared data, you have to call RCU read unlock. At that point, you have to give up and promise to never use again that value of the root pointer that you got. If you want another access to shared data, you start from the beginning. You call ReadLock, you again get the root pointer, which may or may not have changed, and you use it until you call read unlock. You also promise to never access the shared data between the calls to unlock outside of the lock unlock, so between unlock and lock. I'll show you the picture on the next slide. The space between lock and unlock is commonly known as a critical section, so here it's a reader side critical section. And what's not in the reader side critical section is called the quiescent state. That's when the readers do not read shared data in the quiescent state. Now, that's the readers. The writers also have their role to play. Again, remember, there is, as far as we're concerned for RCU, there is only one writer. If I say writers, it means there is some sort of mutual exclusion that, like a baton. I'm the writer now, okay, now you will be the writer, but one at a time. So the writer must do the following. It makes the old shared data inaccessible from the root as a part of its read, copy, and update. So when it did the update, it changed the root to point to the new shared data. The old data is no longer accessible from the root. It's not deleted, it's just not like I pulled the node out of the list. I didn't delete the node, I just pulled it out of the list. If you're starting from the head of the list, you cannot find my new node. But if you had an iterator that was scanning the list, you could still find the node that I pulled out. At some point, the writer has to call, let's call it Synchronized RCU. And what that would do is it would wait for all the readers who called ReadLock before step 1. So before I made my data hidden. All the readers who could see my data that is now hidden. It wasn't hidden for them yet. So I have to wait for them to call read unlock. It's very important that I don't have to wait for all readers ever to stop reading, because that may never happen. I just have to wait for all the readers that saw my hidden data before it became hidden. Well, let me show you on the picture. So here is my writer on the top. The timeline goes left to right. So I have my data 1, and my pointer points to data 1, and I'm preparing data 2. And nobody knows about it. At some point, I'm publishing my data 2, and at the same time, this is an atomic transaction. So I'm hiding data 1 and revealing data 2. And now I have to wait. So what's going on the reader side? Well, let's start from the beginning. The readers all, I only show read-lock and read-unlock for one reader, but they all do this, okay? They all do this, I just don't put it in the picture. So the reader calls read-lock and gets the root pointer. And this is the beginning of the section. The pointer points to data 1, so we'll call it P1. That's all you can get at this point. And you keep using it until you're done, and then you call read-unlock. Another reader thread also gets P1, and another, I haven't changed, so all my readers at first get P1 because there isn't anything else. Now, I publish the new data where this vertical arrow is. Here. I publish the new data, but see, this reader here, when it acquired the root pointer, that was way back there. So you have to see past, present, and future all at the same time, because this guy has P1 as his root pointer. Now, this reader is in a quiescent state. It has nothing. So the real root pointer is now P2, and has been P2 for a while. But one of the readers has P1, still uses it. I cannot delete. Cannot delete what P1 points to. I have to wait for all of the readers that acquired P1 to leave by calling RCU read unlock. Some of the readers will already be on the new version of data, and that's fine. But when the last one that still can see the data 1 leaves, unlocks, now it's safe to delete data 1. I can delete it immediately, I can delete it later, that's my own problem. However, I want to do reclamation. But now I can delete it. So that's RCU protocol. Now let me show you the main idea of how the protocol works. And this is, you can implement it literally like this, or it can be very conceptual. So let me show you the idea, and then I'll talk about implementation. I'm going to count how many readers have currently P1. For now, let's say that it's just a reference count. So first reader called read-lock, and P1 was the current value of P, so I have one reader with P1. Second reader calls read-lock 2, third reader 3. One of the readers exits the critical section, gives up its copy of P1, so 2, but another reader comes in, so now 3, and it goes up and down. At some point, I've changed my root pointer P to go from P1 to P2. Now I have two reference counts, because some readers are still sitting on P1, and the reference count is still 2 or 1. And some readers are now starting to acquire P2, so that reference count goes up. So now I have two reference counts, and they may drop to 0 at some point. Now, when P2, the current reference count, drops to 0, that's not special, because it points to the current live visible data. I'm not interested in deleting it, it's the current data. So 0, the fact that there is no readers doesn't mean anything. But when P1 reference count, the reference count of the old data drops to 0. Now that's special. And the reason is, see, the reference count to P2 dropped to 0 and then went back up to 1. Because that data, any reader can see it, any reader can get it. The reference count of P1 dropped to 0 and it will never go back up to 1 again. There is no way for you to get P1. There isn't actually any P1 in the system anywhere anymore. So now it's safe for me to delete it. Now, as I said, the implementation may or may not have a reference count. The implementation may have multiple reference counts. The implementation may not actually have a reference count at all. But there is a way somewhere to traverse some data structure inside the RCU system, add up something, count something, or add up something, and figure out how many readers you currently have outstanding. So conceptually, there is a reference count. It could be, distributed like as a list of nodes. How many I have a node for every reader. How many nodes I have in the list? That's my reference count. That's one of the implementations. That's, if you went to Ansel Stokes and libguarded, he showed you every reader coming in was putting a node on the zombie list. There isn't a reference count in that system, but if you could let's freeze the system just and have a God's eye, which I can look down on the entire system. I can count the entries in the zombie list. That would be the reference count. The function names vary. Question? No? Okay. The function names can vary. The ReadLock, read-unlock, and Synchronized RC are the ones proposed for standardization. A very common set of names is RCU enter. That's instead of ReadLock, you enter the critical section. Leave, you leave the critical section. And instead of Synchronized RCU, another one that is very common is wait for readers to leave, because that's what you do. You wait for readers to leave. You could have additional functions, and in fact, most implementations, including the one proposed for standardization, do, but those are less universal. RCU has been used in Linux kernel very extensively for many years, much less extensively in Userspace. Kernel does have several advantages. Basically, it knows when all readers go into quiescent space, it runs the threads. It knows how many threads there are, what are they doing, when are they running, when they're not running, and it doesn't need extra memory barriers, the ones that we had on our one of our early slides showing how to acquire data, because the kernel has to make sure when the readers are in the quiescent period, they're not running any instructions, which means something has to synchronize. So at this point, after this point, nothing else on this thread is running. That's the equivalent of a memory barrier, and that's good enough. It doesn't change the basic idea, but it's important to understand the implicit assumptions, what you can and cannot get away with. For example, if you look at the ReadLock in the kernel, you would see that it actually does not have an acquire barrier. It doesn't need one. It's freeloading on some other barrier, but it doesn't mean that entering the critical section does not require a barrier at all. It just means that they already had one, and they're basically taking advantage of it, which is a good thing. It makes your code faster. And they had to have that other barrier. So it's not wrong. It's just if you're trying to understand it, you have to be aware of the implicit assumptions in every RC, in the particular RCU protocol. It kind of does look a lot like garbage collection. And there is, again, some confusing terminology here, because if you open a CS text and look up the definition, garbage collection is automatic memory reclamation. Actually, the word automatic is there. Garbage collection implies automatic garbage collection. Nonetheless, in practice, people talk about user-driven garbage collection. The simplest form of user-driven garbage collection that you find, like in practical talk, is you have a memory pool, you allocate some memory, you create some objects, and then you, instead of deallocating all the objects one at a time, you blow away the whole memory pool. That's basically you're declaring as a user, all of these objects are now garbage, please go reclaim. I don't know a better term than user-driven GC, even though it's kind of like saying round square. If anybody knows the correct term for a reclamation that is triggered by user action, let me know.
I think some papers use compaction.
Not exactly the same, but anyway, come offline and talk to me. So the memory reclamation in RCU is kind of like user-driven garbage collection. There will be a user event that would trigger the reclamation. Okay, I have actually written a Userspace RCU. I'm not going to show the code. It's messy, and the particular implementation isn't actually very interesting. It does use the reference count. I will talk you through the algorithm. Okay, but this is what I get. Read-only and RCU without any writes. So there is a possibility of the writes, but no writes are actually happening. The difference is just within the margin of error, so same speed. Now I'm going to turn on some small amount of writes. There is about 1 write per 100 reads. It's a little slower, but it's pretty good. I have another RCU algorithm. That's what it looks like. This is the one with writes. Without writes, it's still the same. So why are there so many different RCU algorithms? Well, many different implementations. Let me talk you in details through one particular implementation algorithm, and then I'll show you kind of the variations you can do on the subject. So we'll like learn the main melody and then the variations. So here is the idea. The writer will maintain a global integer that is called generation. Sometimes you can find the term epoch. it's monotonically increasing. All the data that you have belongs to a particular generation. The data that is currently live belongs to the current generation, which is the value that is stored in that integer right now. When the writer does an update and makes some data inaccessible, let's stick with our list. So I'm pulling a node out of the list, replacing it with a new node. I will put the old node in, let's say, generally garbage queue. In my case, it's just a list of nodes to delete, and it's another list. But in general, it's some queue of garbage. This stuff I can't delete just now, but I would like to. There is one of these garbage queues per generation. So when do I change generation? Oh, whenever I want to, whenever I feel like it. So I'm doing some number of updates, and then at some points I go, okay, you know what? I'm revving up the generation. All the new updates that come after that will have the next generation, which means they'll go on the next garbage queue. So generation 0 has its garbage queue, generation 1 has its garbage queue, and so on. Now, when any reader that is currently beginning to access this list can only access the current generation, because they can't access anything that has been already put on the garbage queue, not accessible from the list anymore. But any reader that started accessing the list can keep accessing it long after some node became garbage. So what I need to know is how many readers started accessing the list in a particular generation. When all readers that have generation 0 left, my garbage queue of generation 0 can be collected, because no reader that entered during generation 1 could see any of these nodes. Okay, so very similar, but now with this explicit generation. So I have generation n on the left. I'm preparing some new data. I'm publishing some new data. Notice that I didn't rev up generation at that very moment. I could, but I don't have to. These two acts are independent. I can publish as much data as I like within a current generation and then rev up the generation anytime I want. I could have one new piece of data per generation if I want, or 100, or that's whatever I want. Okay. Once I revved up the generation, I have to wait for readers to leave. How do I know when the readers leave? Well, remember my readers, how they were storing the pointer to the data. Well, they don't store the pointer to the data anymore. What they do store is the generation at which they entered the critical section. So when they called ReadLock, I told them, okay, you're calling ReadLock, current generation is generation n. Hold on to that n, you'll need it. When they're calling readOnLock, they're saying, I am a reader from generation n. On the writer side, I'm counting, okay, generation n has been superseded by n plus 1. I have 3 readers from generation n. 1 just exited, 2 just exited, 3 just exited. Okay, go to town, collect garbage. So last reader from generation n exits. Now I can delete garbage. So the implementation, again, this is the slide code. You might ask me, okay, what was the difference between the algorithm 1 and algorithm 2? Which slide code is this code for? And the answer is actually both. The difference is in the little details that don't fit on the slide. The skeleton is the same, but it's the variations that make it different. Okay, so my global atomic generation. I have an array of atomic reference counts for some maximum number of generations. Okay, what that is and how do I deal when I overfill the number of generations? Again, that comes under the variation subject. So let's for now assume it's large enough, never happens. I have this opaque type called handle. And somewhere inside there is a generation. And what the reader gets from the ReadLock is that handle. And you can't really do anything with it other than you can surrender it to readOnLock. But that tells the writer that you are surrendering access to a particular generation. So ReadLock increments the reference count on that generation and packages the handle with the current generation. And readOnLock extracts the reader's generation from the handle, decrements that reference count. That's all we do. Now, these are default operations on atomics, which means they're using sequential consistency. I told you on Monday sequential consistency is expensive. If you have to use atomic, you should try to avoid it. Yes, in reality, you will avoid it. The problem, why am I not showing you the exact memory barriers? Well, the actual reason is I can't. Synchronization protocols on multiple atomics are tricky, and which barriers you need to take exactly where depends on the very subtle details of actually how you synchronize. So typically there will be one sequentially consistent access in this whole mess. Lamport algorithm relies on that. There's one acquire barrier, one sequential consistent, and one release. There are some synchronization protocols that use an additional atomic and get away with no sequential consistent memory access. They kind of fake it by a combination of release and acquire. It may or may not be more efficient. That's, you have to measure these, but that's a lot more code than I can fit on the slide. So assume that the memory barriers are finely tuned to the particular synchronization protocol, but it would take me another hour to just explain one of those. So I'm, simplified slide code. Just uses atomics. What do the writers do? Well, the writers are very simple. Eventually, you'll call Synchronized RCU on the writer. So when that happens, I'm going to scan all the generations, stopping before the current one, because I can't reclaim the current generation. And I'm going to look at reference counts. And if a reference count of a particular generation is not 0, I'm going to wait until it becomes 0. And if it's 0, I'm going to reclaim all the memory on the garbage queue. And then I'm going to move on to the next generation. You can't jump. If a reference count of generation 0 is, so generation 0 is still some readers alive with generation 0. But the reference count of generation 1 has dropped to 0. Well, you can't jump a generation. You have to collect them in order. Because remember, all the ones that were earlier can see everything that came after that. It's just all the ones that came later cannot see what was removed before. But all the ones that came first, they see everything that was there. Okay, so that's basically how synchronized RCU can work. Okay, so all RCU implementations will have these 3 functions under some name, like the standard names or enter, leave, wait for readers to leave, or whatever you may call it. They'll have something, they'll have that. After that, you can get creative. So let me show you how you get creative. One thing you may want to do is you may want to minimize read-lock and read-unlock. Now, that's not the only trade-off you may want to make. For example, you went, I hope, to Ansel's talk yesterday to see his presentation of libguarded, very convenient library for encapsulating these things so you don't start seeing past, present, and future all at once in your head. He made a different choice. His read-unlock collect actually does the garbage collection. It reclaims the memory. So his read-unlock is not as cheap as it could have been. Maximum throughput of readers wasn't the design goal. He did the right thing for his design goal. Now, if I wanted maximum throughput of readers, I would do read-unlock as efficient as possible. And I might impose some additional restrictions on that. So why would be the reader overhead? Well, you could make read-unlock heavy, or you could make it garbage collect. Let's say you didn't do that. There's still overhead. You have to read the generation number, and in my schema, you have to increment the reference count of the generation. That's read, modify, write on a shared data, because all the readers are doing atomic increments on that shared data. And then I have to acquire read the root pointer. Acquire, you've seen my graph of performance of atomic operations before. Acquire, read, not so bad. The read generation number, not so bad. Read, modify, write, that's like at least an order of magnitude slower, probably more. And the reason that's slower, it's a cache contention on the cache line that the reader is writing into, the reference count. Well, the problem is the reference count is shared between all the readers. Here is one possible solution. It's not the only one, but I'll show you just this one. Each thread has an ID. Each thread has its own reference counter for that thread ID. If you go to the rather extreme measure of doing it, please pad it to the cache line. You don't want the false sharing here, to go to all this trouble and then die because your reference counts are in adjacent 8 bytes. No, space them up by 64 bytes on if you're on x86 or whatever your cache line is. Well, you need consecutive reader thread IDs 0, 1, 2 for this to work, which means you actually have to somehow register the threads with the RCU system. The RCU system has to know how many threads you have so it can allocate this array of reference counts. Well, if you don't have that, there is still, it's not quite as good, but you don't despair completely. You can, for example, take your random large thread ID, hash it into an interval of, I don't know, 128 or whatever, and use that hash to index the reference count. It would have to be atomic. You would have to have shared read modify writes, but you would have much fewer threads actually colliding, because readers will be scattered across all the, if your hash is good, across all 128 reference counts randomly, so actual contention on the reference count would be much less common. That actually moves a lot of work onto the writer, because now writer, instead of just accessing one reference count, has to access them all and add them all up. The good thing is, how accessing multiple reference counts that change all the time, ooh, scary, not atomic. The good thing is the reference counts for the old generation only go down, they don't go up. So once they all reach 0, that's it. So you can say, okay, this one is 0, I don't need to come back to this. It'll never, always will be 0. And this one is 0, and this one is 0. They're all 0, okay. Do I need to go back to the beginning and check the first one? No, I don't. And that's what makes the schema workable. On the readers, you have this. This is a design question. Can you nest critical sections? Can you call ReadLock inside ReadLock? Very often the answer is no. I can live without nested critical sections. You can actually simplify your life a little bit. You don't need a full reference count. You can just, for every reader, you can just know, is it in the critical section or not? So instead of having an actual reference count, you just have one, basically a reference count for this reader is either 1 or 0 then. Now, okay, so you can do that if you don't need nested critical sections. If you can't register threads, you can do the hashing of thread IDs. Some of the interesting things you can do on the writers. The big distinction between RCU implementations is, if you read about them, with deferred deletion and without. And what they refer to is a very generic RCU implementation would have a callback, basically. This is how you delete this piece of data when you get to it. You enqueue this callback, so it's deferred. And when it's safe to do it, it gets called. So call RCU is the common name of the function that enqueues it. So you could call RCU, you give it the piece of data and how to delete it, the functor. It doesn't actually delete it. It just enqueues it for future deletion. A big distinction on the writers, which is actually the difference between the two cases that I have shown you, the fast and the slow one. At least under that workload, they were fast and slow. It's not that one is always slower than the other. Granularity of updates versus granularity of the cleanup. How many updates go into one generation? You don't always have like strictly generation. You may not have an integer that is monotonically increasing, but you still have the equivalent of the generation. Like when you put nodes on the zombie list, that's your generation just rolled up. So granularity of updates versus granularity of the cleanup. Do you clean up everything, like you wait and then you clean up all the garbage, and you wait until you can clean up all the garbage? That's one way. Another way is you can periodically ask, okay, do I have any generations that are not visible by any readers now? I don't want to wait. I just want to know if any of the readers happen to already left that generation. If yes, I'll reclaim that memory right now with no waiting. If not, I'll keep piling up garbage. Of course, eventually you'll run out of memory, but and then you have to wait. But you can do this for a while. Guard objects, where you basically have a root pointer for every for every data, more overhead, but much less unclaimed garbage because you reclaim faster. So I've shown you these two plots separately. Now they're on the same plot. The difference between the fast RCU and the slow RCU that I was shown before, in my case, was one had short generations, one had long generations. That was all the difference. Okay, let's look at some performance just so you get a flavor for it. We're coming up on the end of it. So the baseline at the top, only reading, no synchronization. That's when I know that there are no writes. You know, this is the ideal. I want my reads to be like that. The line that goes kind of almost parallel to it, let's see if I can get it. Okay, this one here. That's my RCU. So there is about 1 write per 100 reads here. Lock free is on the bottom. Read-write locks start good and then they stop scaling. And libguarded is somewhere in the middle. As I said, high throughput wasn't the design goal, so don't take it as a criticism of that wonderful library. Non-blocking readers were the design goal, not high throughput on the readers. Okay, let me put it to a stress test. I'm now going to really crank up the writers. Now I have one thread doing writes at the maximum rate that that thread can sustain, and the readers. Well, so all the RCUs are going way down. The one that is optimized for maximum reader throughput basically holds its own as good as it can, but they're all suffering. Okay, well, let me skip this because I'm out of time. Okay, so one kind of final point, just because again it requires you to turn your head on sideways. What happens if the readers hold on to their generation or their handle or their lock like for a very long time? Well, usually there is nothing you can do about it. There are some implementations where you can actually force reclaim. So what does it mean when you force reclaim? The writer decides to go and forcibly delete the memory. The readers will be left in an undefined state. Well, that's kind of bad unless the readers can handle it. The one scenario is where you don't actually delete the memory, meaning like you don't release it to the system. You have your own like memory block and you just reuse it. And the readers can handle inconsistent data. They won't crash. They will get some results that they don't like, but they have a way of detecting that. So the other option is that the readers need consistent data, but they can verify. So for example, this read unlock, when I surrender the handle, I can ask, did the handle expire? Did the writer forcibly reclaim the memory of that generation? If the answer is yes, I have to drop everything that I have done in that critical section, reacquire the root pointer and recompute, because what I have done is garbage. Not in the same sense as the garbage. And actually, I once worked on an application where it was okay for the readers to crash. It wasn't threads, it was shared memory processes. And the system just restarted the process. They were all stateless. If it crashed, it got restarted, and that was fine in that particular application. Okay, so when should you consider using RCU? So kind of the landscape of RCU. Two axes. How often do the updates happen? And how much consistency, how consistent view of your shared data do you expect? The RCU paradise is when updates almost never happen and you don't care if the data is inconsistent. If you need perfect consistency and updates are hammering your system all the time, it's not going to work. Somewhere in the middle, it's going to slowly lose efficiency, as I have shown you on these plots, and the ones optimized to sustain higher write speeds will lose efficiency, not quite as bad as the ones that are not. So it affects the choice of your RCU algorithm. Okay, just by way of comparing with some other popular mechanisms, hazard pointers do something very similar to RCU. They have different features in regard of how much memory, how much garbage is sitting unreclaimed. Their biggest problem isn't really that. Their biggest problem, they're hard to use. Not hard to write. I mean, hazard pointer class isn't that hard to write and somebody has already done it for you. They're hard to deploy in your algorithm, whereas RCU is pretty easy. Identify your access to the shared data, call ReadLock, read unlock, and periodically involve garbage collection on the writer. Atomic shared pointer. easy as long as you have a way of handling circular references. But it's lock-free, but it's much slower than the RCUs because it uses relatively expensive read, modify, write atomic instructions and more than one. Questions? Yes?
In your model of, so you have a root pointer and you have an array of pointers to blocks of data. And when you want to start a new generation, do you need to make a brand new copy of the array of pointers to make parts of that inaccessible?
Okay, so the question is about my deck-like container, and let's say I didn't want to keep all the reference blocks forever. I actually wanted to reclaim memory using generational RCU. Okay, so how would I do it? What would be in each generation? Let's say I rev up the generation every time I have to change the reference block. That'd probably be a good decision because it doesn't happen very often. I have a lot of data, new data added before I have to change reference. So I rev up one reference block per generation. My readers would have to call ReadLock and acquire the generation. And I have to wait. So each of my reference blocks is now tagged by the generation.
What are you calling reference block?
Reference block is a block of pointers.
Okay, so the whole array.
Yeah, there is just one contiguous array of pointers. So there is an array of pointers that's what I called reference block. That's a block of pointers. So that guy is tagged by the generation. And let's say I'm revving up generation every time I change that reference block. So ReadLock gives you the generation of the current reference block. When the last reader surrenders that generation, the writer can delete the reference block of that generation. I would just have one reference block per generation. The last read unlock with that generation either deletes it on the reader side or triggers the deletion on the writer side, depending on whom you want to pay for that call.
Thank you.
Yes?
So in your last performance chart, you showed that if there was a writer that was writing at a like maximum throughput, that then the performance suffered of RCU.
Yes.
But your RCU implementation was still getting the best performance out of all the ones that you showed. But in the chart at the end where you said in what use case should you use it, would that be some case that something besides RCU would be better? Like, is there some other?
Well, so in that case, first of all, as you saw, only one RCU implementation sustained it. Mm-hmm. You know, the slow RCU, the slower RCU, the libguarded, and the read-write locks were basically running at about the same performance here. In fact, read-write locks slightly outperform libguarded. The minimum overhead RCU was the one that was still pulling ahead, and the price is it accumulates more garbage. Because that's basically how I gain performance, by batching deletes. Fundamentally, that's the trade-off. So with that trade-off, the longer you can keep it. Like if you didn't have to delete anything ever, you would actually go all the way back up to the top, like almost, would be like within 15% of the top. So as long as you can sustain that trade-off of memory, you can keep the performance. When you have to throttle it down, you have basically one of two options. You can throttle updates. So that's, I didn't talk about it, but another option is on the writer side, you can actually throttle the updates. You can say, okay, too much garbage accumulated, readers haven't left. You writer now switch from writing to collecting garbage. Oh, and by the way, you have to wait.
Yeah.
That naturally throttles the updates.
Yeah.
That may or may not be acceptable. Updates are piling up, you may not be able to throttle it. If you are, it's a solution. If you're not, you basically, now you have essentially a writer thread, a reclaiming thread, and then the synchronization of the two of them becoming contentious. Here I just had one thread still. Reclamation was in big batches, so it's actually cheap. You cannot delay updates, let's say. You have to sustain all the writes. So your writer thread and your reclaimer thread are now separate. they are now in contention because they're both running at maximum bandwidth. So now the whole thing slows down even further. Now, I don't know if it kind of the lock-free list would do it. It would just eventually it would be just as slow as RCUs. I don't think it would ever be like faster. But you may have to reevaluate your design decision. You may have to give up sequential consistency somewhere, go for like a statistical queue. If you're doing queuing, some event queue, and that's what you're after, you may have to basically give up sequential consistency on the queue and go for probabilistic queue. Those are faster at the expense of sequential consistency.
But in the example you gave of that there was a writer that had a high throughput and you cared about consistency, you said you wouldn't be happy with RCU. But what would you be happy with?
You are allowed to accumulate. So
I see.
In this test, in that second line from the top accumulates maybe 20–30% extra memory in this test. And that's the best I can do with that implementation. And it's also kind of spiky. It accumulates and then it collects it in batches. If I needed even higher throughput of updates, also my writer periodically pauses to do reclamation. It's dying it in small batches, so I'm not holding updates for very long, but the writer actually has the second task of doing the reclamation, of calling the freeze. If that's not acceptable, if you need even higher throughput than that can deliver, it's going to be even slower. It's going to stress you even harder.
Okay, thanks.
Yeah, so eventually you can squeeze RCU out of usability or make it so hard to write that by this point it doesn't look like RCU anymore. It looks almost like a lock-free list or a hazard pointer.
Hi, I'm actually surprised to see that you have so much difference between the read-write-lock and your algorithm, and both need to pay the price for counting the readers.
Well, remember, these are pthread read-writer locks. These are not the best read-writer locks you can possibly come up with.
Okay.
So that's one. I have not tried to, for example, like on Monday, I have shown you the difference between POSIX mutex and my own spin lock, the best I know how to write. And it's like more than an order of magnitude. I haven't done the same with read-write locks. I probably could have.
And you get similar.
I don't know what I would get.
All right, that answers the question.
But
yes, so this is against the POSIX.
This is against the POSIX read-writer logs. Questions? No? Okay. Well, and you can also just find me offline. Thank you again for coming and for listening. I hope you got somewhat confused.